My name is Oluwatosin Ogundipe, and I'm being supervised by Professor Eric James Mackay and Professor Ken Sopi of Heriot-Watt University. Today, I'll be talking about halite deposition during CO2 injection in saline aquifers, study of its formation and management. This work is being sponsored by Energy Simulation. For the background, CO2 injection in saline aquifers causes precipitation of halite that affects the injectivity of wells. Evaporation of brine leads to formation dryout and halite deposition. Therefore, effective porosity and permeability are impaired. Now, these are download images of halite deposits, and this is an SEM photomicrograph of precipitated salt. To the objectives now. The objective of this work was to develop numerical models of CO2 injection in intermediate and high salinity brines, evaluate the effect of capillary pressure on the amount of halite precipitated, evaluate the impact of lodged or displaced halite on porosity, permeability, and injectivity. Then evaluate the effect of increasing and decreasing CO2 injection flow rate on the size of the dryout zone and halite precipitation. And the last one, to what extent does interplay of viscous, capillary, and gravity forces lead to localized precipitation of salt near the wellbore? Now we go to the methodology. I used numerical simulations and they were performed using GEM compositional reservoir simulation software. 1D and 2D radial models of CO2 injection into a candidate saline aquifer were developed. The 1D is 100 meters thickness, and the 2D is discretized into 10 layers of 10 meters thickness each. The grid is half circle so that the slice of the model can be seen. It's half circle here. And calculations were made to determine the size of the dryout zone, porosity, permeability, and injection and injectivity changes. So this is the 1D model, flow in one direction. That's why it is called 1D model, because the flow is in one direction, only horizontal flow, no gravity. For the 2D flow, we have flow in two directions when we included the gravity component. So the flow here is both vertical and horizontal, and that's why it is called a 2D radial model. And now to the results. Now we consider the effect of capillary pressure, the 1D scenario. We considered the effect of CO2 injection flow rate, 1D scenario. Then we also consider the effect of viscous, capillary, and gravity forces, 2D effects. For the effect of capillary pressure, the 1D scenario, what we see here is that the size of the dryout zone, colored red, is pushed back where capillary pressure is included in the model. That is this picture. We can see that capillary pressure is being, because the capillary pressure brings in more water into the system and the dryout zone is limited in this system. And that's because of continuous backflow of brine, constantly replenishing the zone, resulting in more deposition. For the one colored in the red, we see that the dryout zone is more extensive here, and that's because in this case there's water evaporation but no capillary pressure. So for the no capillary pressure and evaporation, the porosity loss is about 5%, and permeability loss is 11%. But when we now included capillary pressure and evaporation, porosity loss is now 50%, and permeability loss is 81%. So we have more damage to our reservoir when we included capillary pressure and when we had more evaporation. So for the effect of the CO2 injection rate, now on the left hand side we have a higher injection rate, and the dry out zone here is 10.7 meters. On the right hand side, we have an injection rate of a low injection rate of 19,050 is a lower injection rate, and we had a dry out zone of 0.7 meters. For the higher injection rate, viscous forces dominated, suppressed capillary pressure. But for the low injection rate, we see that the capillary dominated forces overcame the viscous force. So for the high injection rate, that's the left hand side, there was an increase in the dry out zone, 10.7 meters, which you can see here. And there's a decrease in salt deposition. Porosity losses to 21%. That's because the viscous forces was able to push away brine from the wellbore region, and that's why we had we didn't have so much damage near the wellbore. But for the low injection rate, this one on the right, there is a decrease in the dry out zone, and that's because brine replenished the system because of the capillary pressure, dominated system. So we have that the dry out zone is 0.7 meters, but we have that there is an increase in salt deposition in this case because of the constant replenishment of the near wellbore region. With more brine, we had more salt depositing in the near wellbore region, and there was an increased salt deposition of 90%. So the well here is almost completely blocked because of the increase in brine influx due to capillary pressure. So we now also consider the effect of of viscous forces, capillary and gravity forces. What are the interplay when we included gravity, the 2D effects? On the left hand side, a point of contact between the dry gas and the brine develops in the bottom layers, highlighted here. Here's highlighted, resulting in dry out, localized precipitation, and also occlusion. So here we had, because of the point of contact, we had damage at the bottom of the well. On the right hand side, there was more gravity segregation. The dry out zone moved up the well, and we had that the point of contact between the dry gas and the brine moves further up the well, as highlighted here, causing complete salt blockage in the upper layers. But in the lower layer, because of the influx of the brine, we had some self-healing that took place at the bottom of the well in this case. And the reference used for this work is the paper written by Talman and others. Talman or physical and chemical characteristics of salt recovered from an active CO2 injection well. I want to thank all our all my sponsors: BKU, Champion X, Chevron, Clariant, CMG, Equinor, Energy Simulation, Halliburton, Repsol, PTDF. I want to thank also Shell, to thank Vedanta and Wintershell for this work. PTDF is a body that sponsors, in a Nigerian body that's sponsored by my scholarship, and I want to thank them for their sponsor. This is what I have today. This my short presentation. And I would like to end it here. Thank you very much.